Welcome to the Automate workshop. Hi, I'm David. In previous modules, we looked at the basics of electricity, series circuits, and parallel circuits. These modules are designed to increase your knowledge and understanding of electrical circuits. We'll continue our journey with series parallel circuits, voltage dividers, and relays. The definition of a series parallel circuit is a circuit that contains some loads connected in series and other loads connected in parallel to form multiple paths. These two circuits are both series parallel. We'll examine each one and see the differences between them. This circuit has globe 2 and 3 in parallel with each other and in series with globe 1. Will all the globes be the same brightness? Let's work it out. When determining how a series parallel circuit works, it is necessary to look at each part of the circuit separately. I want to find the voltage drop across each globe. The equivalent resistance of globe 2 and 3 from our parallel resistance formula is 3 ohms. I can now look at the circuit like this. Calculating the voltage drop is a matter of finding the current and multiplying it by the resistance. The current equals voltage divided by resistance. That's 12 divided by 9, which equals 1.33 amps. Voltage equals current times resistance. Globe 1 will have 6 times 1.33, which equals 7.98 volts. Globes 2 and 3 will have 3 times 1.33, which equals 3.99 volts. Seeing that globes 2 and 3 are in parallel, they will have the same voltage drop. So globe 1 will be the brightest. What would happen if globe 1 was to fail? Because it's part of a series circuit, the current would stop flowing due to the open circuit. If globe 2 failed, what would be the result? Globes 1 and 3 would continue to work as globe 2 forms part of the parallel circuit with globe 3. An interesting thing now occurs. Globes 1 and 3 are now in series, and because they are the same resistance, they will share the voltage equally. So globe 1 goes from 7.98 volts to 6 volts, and globe 2 goes from 3.99 volts up to 6 volts. In other words, globe 1 will get dimmer and globe 3 will get brighter. This is the circuit. If I remove globe 1, all of the globes go out. And if I remove globe 2, as calculated, globe 1 gets duller and globe 3 gets brighter. This circuit, although still a series parallel circuit, is different from the previous one. Globes 2 and 3 are in series with each other and in parallel with globe 1. This time, will all the globes be the same brightness? The answer, of course, is no. Globe 1 is connected between B+ and ground, so we'll have a voltage drop of 12 volts. Globes 2 and 3 are in series, and because they are the same resistance, we'll share the voltage equally. 12 divided by 2 is 6 volts each. If globe 1 was to fail, because it's part of the parallel circuit, the other two globes will not change. Failure of either globe 2 or 3 results in the other globe not working, but will have no effect on globe 1. If I remove globe 1, it has no effect on globes 2 or 3. And if I remove globe 2, globe 3 goes out, but has no effect on globe 1. Two series parallel circuits with the same loads, but they behave completely differently. The operation of series parallel circuits depends on how they're connected. Voltage dividers can be used in a number of automotive circuits. They essentially divide the supplied voltage into a number of smaller voltages. In this example, if the two resistors are the same value, then V out will be 6 volts. In this example, V out would be 8 volts when compared to ground. We can do more with these circuits. If I connect each resistor joint plus the 12 volts and ground to a switch, I can then have 4 pieces of data going out one wire. If this wire is connected to a module, it'll be able to know the switch position by the voltage input. I could go one step further and have 7 pieces of data, or even another step and have 13 pieces of data. I could keep going as long as the differences in each voltage step is recognisable by the module. Here we have a voltage divider circuit. And as you can see, the voltage increases evenly. That's because the resistances are even. If the resistances weren't even, the voltages would step up unevenly. Either way, the module can be programmed to understand what these voltages mean. There's one drawback to this type of voltage divider. It can only send one piece of information at a time. This can be overcome by this type of voltage divider. With all the switches open, the voltage to the module is at its minimum. Closing switch S1 will bypass R1, so Vout will go up. The same applies to all the switches. Each one will cause a different voltage in Vout. The beauty of this voltage divider is that it can be designed to not only send a different voltage for each switch, but for every combination of switches. Relays are components that use a small current to switch a much larger current. They can also be used to electrically isolate one circuit from another. The 4-pin relay is one of the most common types and can be wired in one of 4 ways. The coil of the relay can have a switch to positive voltage on one side and a ground on the other. The load can be positively switched with a permanent ground as shown in the diagram. When switch A is closed, the coil will create a magnetic field that will attract the armature, closing the relay switch contacts. B+ will be now connected to the load. Here the coil is connected the same way, but the relay contacts now supply a ground to the load. When the switch is closed, the coil will create a magnetic field that will attract the armature, closing the relay contacts. Ground will now be connected to the load. This time the coil of the relay has a positive voltage on one side and a switch ground on the other. The load is connected the same, with the relay providing the ground connection. When switch A is closed, the coil will create a magnetic field that will attract the armature, closing the relay switch contacts. A ground will now be connected to the load. In this last example, both the coil and the relay contacts have a positive supply. The coil has a switch to ground, whereas the load has a permanent ground. When the relay contacts close, the positive supply will be connected to the load. Here I've got a relay circuit with 2 globes. I'm going to measure the coil current. And we've got about 0.14 of an amp. I'll measure the load current. And there we have a little bit over 1.2 amps. I'll put another couple of globes in the circuit. I'll do the same measurements again. Coil current, pretty close to 0.14 of an amp. And load current, this time has gone up to just over 2.4 amps. A small current switching a much larger current. The small current, or the coil current, is not dependent on the load. We've shown you how different connections can have different effects in various circuits. I've shown you how we can send multiple pieces of information down one wire using voltage dividers. And I've shown you the 4 configurations of a 4-pin relay. As with any of our modules, if you're not sure of anything you've seen, go back and review it again. And always remember, training is the key to your success. Bye for now.